This is muscle fiber. It's a simple diagram of a muscle fiber. You have the sarcolemma, which is the equivalent of the cell surface membrane of the muscle fiber. A muscle fiber has many nuclei, or has many nucleus, and it's further divided into a myofibril, which is the structure you see here. And then that surrounding the myofibrils are the sarcoplasmic reticulum, the SR. And then you have myofilaments, which are made up of actin and myosin. Now within the muscle fiber you have sarcoplasm, which is the equivalent of the cytoplasm. And then you also have many mitochondria to produce ATP. This is a zoomed in version of the myofilaments. You have the A band, which is composed of thick and thin filaments.
Hey, did you guys know
you have the H band, which is only... Yeah. So the H band is made up of thick filaments. The Z line is where all the thin filaments meet, and then the I band is composed of only actin filaments or thin filaments. The M line is the middle line. From one Z line to the next is one sarcomere. The beginnings of muscle contraction starts off with the neuromuscular junction.
Blocked by troponin. So the troponin basically covers the active sites until
and here, similar to how the synapses work with the impulses, you're going to have the same thing happening. The action potential is going to flow down here, stimulate the voltage-gated calcium channels to open. Calcium comes in. It causes the vesicles to fuse with the membrane, and then the ACH within that is released into the synaptic cleft via exocytosis. It diffuses across the synaptic cleft to bind with the protein receptors on the sarcolemma. So this is the sarcolemma.
This carries on later to
then what occurs is that the sodium channels are stimulated to open, influx of sodium comes in, that depolarizes the sarcolemma, the impulse travels down the sarcolemma to the T-tubules, and then the electrical impulse from the T-tubules causes calcium channels to open in the SR, or the sarcoplasmic reticulum. And then once those channels open, the calcium ions flow down their concentration gradient, down a steep concentration gradient into the sarcoplasm. So the calcium ions that are now in the sarcoplasm surrounding other myofibrils binds with troponin and causing...
attaches to the active site.
So the calcium ions binds with troponin, which is on the actin filaments, causing troponin and tropomyosin to change shape, which exposes the binding site of myosin. So that's on the thin filaments. The thin filaments are the actin molecules. They wound together, forming a chain.
They're released basically back to its original.
So the myosin, which has a globular head, is going to bind to the actin, the exposed binding site on the actin filaments, and it's going to form cross bridges, which I'll draw here.
This is the whole muscle contraction.
Then what occurs is, and the following is known as the power stroke, is that the myosin head. So once the myosin head attaches to the binding site in the actin filament, the myosin head is going to pull the thin filament towards the M line. And then it's the myosin globular head acts as an ATPase, which hydrolyzes ATP, and the energy that comes from that hydrolysis causes the myosin head so myosin then lets go of the binding site and pulls back. The energy causes it to tilt back to its previous position, and then binds to another binding site on the actin filament. And what happens during muscle contraction is the sarcomere contracts, it gets shorter.